Hello dear students, welcome back in this video lecture series. My dear friends, we have started the discussion of noble gases. We have already discussed why we cannot say these gases as inert gases or rare gases. Then the uses of all these noble gases that I also covered. Today our topic of discussion is compounds of xenon. So these xenon compounds gives an idea that these noble gases are not inert actually. Means number of different types of compounds can form by the xenon element with fluorine and oxygen. Okay, so both fluorine and oxygen are electronegative elements in the periodic table, with fluorine ranking number 1 having 4.0 electronegativity on Pauling scale, and second one is the oxygen, which is having 3.5 electronegativity, and this xenon element is able to form fluorides and oxyfluorides with fluorine and oxygen atoms. Okay, so first of all we will see the xenon fluorides. First of all we have to study about xenon fluorides. Xenon fluorides. Okay, now different combinations of this xenon element with fluorine gas can be possible, and this xenon fluorides, that's why gives rise to three types of fluorides, namely xenon difluoride, xenon tetrafluoride and xenon hexafluoride. Okay, so XeF2, then XeF4 and XeF6, that is difluoride, tetrafluoride and hexafluoride. Three types of xenon fluorides can be possible by the reaction of elemental xenon or xenon gas with fluorine gas in different proportions of xenon and fluorine gas at different conditions of temperature and pressures. Okay, let us see first of all the synthesis of xenon fluoride. Okay, so this xenon gas, when it combines with F2, in this case both are gases at a temperature of 400 degrees Celsius and 1 atmospheric pressure. 400 degrees Celsius and 1 atmospheric pressure, there is a formation of XeF2, that is xenon difluoride is formed. In this case, when we reacting xenon and fluorine gases, we have to take this xenon gas in higher proportion as compared to fluorine. Otherwise, xenon difluoride, instead of formation of xenon difluoride, tetrafluoride and hexafluoride may be formed. Okay, so that's why to form or to synthesize xenon difluoride, we have to take this xenon gas in higher proportion. Okay, now such reactions, due to the presence of fluorine, such reactions are generally done in nickel vessels or nickel sealed tube. The nickel vessels are made in such a way that they are coated with nickel fluoride. Okay, the reactions of these xenon and fluorine are not generally done in regular glasswares, because we know that fluorine is well known for the etching process of the silica glass. So that's why generally glasswares are not used for this reaction, and nickel vessels are therefore used for such type of reactions. Okay, now when we use when we use this fluorine gas in higher proportion, then there is a chance of formation of xenon tetrafluoride and hexafluoride. For example, when this xenon gas in reacts with twice F2, that is, this is in higher proportion, okay. So at 600 degrees Celsius and 6 atmospheric pressure, okay. So the total pressure of this both of the gases should be 6 atmosphere or more than that. The resulting species is XeF4, in which the ratio of xenon to fluorine is 1:5. The ratio of xenon to fluorine is 1:5. Now the third species, that is xenon hexafluoride, will be formed by the reaction of xenon gas with thrice of F2. Okay, so we have taken these 2 and 3 only for the balancing of chemical reactions. This does not means the proportion of this xenon and fluorine. Actually, the product is this, in this case, is xenon hexafluoride. 1 xenon plus 3 into 2, 6 fluorine atoms are there, okay. But here the ratio of xenon to fluorine for this reaction is 1:20, okay. So the fluorine is taken in large excess, 1:20 proportion is there for the formation of xenon hexafluoride, okay. Now so this is the what we called synthesis for the xenon fluorides, when we take only simple gases, that is xenon gas and fluorine gas, in different proportions. The conditions for the formation of xenon hexafluoride is temperature is 300 degrees Celsius but with high total pressure. So as total pressure is very high, the temperature condition required for the formation of xenon hexafluoride is less, okay. So this is the what we call the xenon difluorides and their xenon fluorides with their synthesis or preparation methods, okay. Then we have to see the structures of these xenon fluorides, okay, and these structures can be explained on the basis of VSEPR model, okay. We have already discussed this model in case of interhalogens, okay. So structure of XeF2, okay, xenon difluoride. So we know that, dear friends, this xenon atom is the central atom in this xenon difluoride according to VSEPR model. First of all, we have to think about the central atom. So the central atom is xenon in this case. Outer electronic configuration for the xenon is 5s2, 5p6 and 5d0, okay. That can be written in orbital boxes. This is 5s2, this is 5p6 and 5d is totally empty. D orbital, D subshell is having 5 orbitals, 0 electrons are present in D subshell, okay. So these electrons present in the one of the p subshell, one of the p orbital, get excited to empty d orbital, okay. So excited state electronic configuration is 5s2, 5p4, 5p5, 1 2 3 4 5. One of the electrons get excited to empty d orbital, okay. 1 2 3 4 and 5, okay. So in this case, look at this picture, orbital picture. This is 5s2, 2 electrons fulfill. This is 5p5, okay, and this is 5d1 now. So all these are all these orbitals are fulfilled. Along with these 3 filled orbitals, these 2 orbitals, okay, so 1, 2, 3, 4 and this 5th, so 5 orbitals combines together, they get hybridized, and this type of hybridization we call it as a sp3d. sp3 hybridization takes place. So hybridization takes place, and it is sp3, one s, 3p and one d orbital is there, sp3d orbital, okay, and there is a formation of 5 hybrid orbitals, 1, 2, 3, 4 and 5, okay. So all these are sp3d hybrid orbitals, okay, and in these sp3 hybrid orbitals, the 3 orbitals are having lone pairs 1, 2 and 3, while 2 are having single electrons. So these orbitals having their single electrons, okay, combines with fluorine atoms. So I am drawing this fluorine electron by dotted arrow, okay. So this is one fluorine sharing of electron of this fluorine with this sp3d hybrid orbital of xenon, okay. This is another fluorine, okay. So central atom is xenon and 2 fluorine atoms shares their electron with the unpaired electrons present in the sp3d hybrid orbital of central xenon atom, okay, and there is a formation of XeF2, that is xenon difluoride, okay. So the number of hashtag is used for number of lone pairs, in this case 1, 2, 3. Number of bond pair is used, in this case it is 2, okay. So the 3 plus 2, there is a total is equal to 5, okay, and steric number, we call this as a steric number. Steric number, in this case 3 plus 2 is 5, and according to VSEPR theory, if the steric number is 5, okay, the possibility of geometry, electronic geometry is trigonal bipyramidal. So trigonal bipyramidal geometry is consistent with the steric number 5, okay, and hence we can call this the electronic geometry of the xenon difluoride is trigonal bipyramidal. But to minimize the repulsion between these bond pairs and lone pairs, these bond pairs occupy the axial position of this trigonal bipyramidal shape, and these 3 lone pairs are occupied by the planar triangular face, okay, and hence we can show this like this is one of the lone pair, second lone pair, and this is the third lone pair, okay. They form a triangular base, okay, triangular base with xenon atom at the center, okay, 1, 2, 3, like this we can say 1, 2, 3, okay. The central atom is xenon, and one fluorine atom, 2 fluorine atoms taking the axial position of this trigonal bipyramidal, 1, 2 bipyramidal. This is the shape of the molecule. So electronic geometry as per the VSEPR model is trigonal bipyramidal, but while dictating the geometry of the molecule or the shape of the molecule, molecular geometry of the molecule, we neglect the lone pairs, and hence the shape is linear. The molecule is linear, FXCF. So molecule is linear with a bond angle 180 degree. Okay, so this is all about the xenon difluoride. So look at this. This is, I have explained in detail the formation of this xenon difluoride molecule. Okay. Now the remaining molecules, that is tetrafluoride and hexafluoride, they can be explained in the same way that we have explained the difluoride molecule. Okay, so means we are using here VSEPR model. Okay, now the structure of xenon tetrafluoride can be explained in the same manner. We have to we can say, or we can show, write the same explanation about this. Okay, and only change is there, as there are 4 fluorine atoms, so means that in the central xenon atom there must be 4 unpaired electrons. In the central hybridized xenon atom orbital, that the xenon must have 4 unpaired orbitals having unpaired electrons with 4 in number. Okay, means we must show another excitation of the p orbital. Okay, so this p orbital electron gets excited to this, and this p orbital get excited to this, and we have this situation. Okay, so 2 p orbitals are get excited to the empty d orbitals, and that's why we are having 1 2 3 4 empty orbitals, and that's why 1s 3p and 2d orbitals get hybridized, and they are giving sp3d2 hybridization. Okay, so we have to add one electron, one orbital, and this is the case. So 4 fluorine atoms, 1 2 3 and this is 4 fluorine atoms shares their electron with the sp3d2 orbital of the central xenon atom having unpaired electrons. Okay, so this is the case of xenon tetrafluoride. Now number of lone pair in this case are 2, number of bond pairs in this case 1 2 3 4. Okay, so 4 bond pairs are there, and hence steric number is 4 plus 2 6. Steric number is 6. Now as steric number is 6, so the expected electronic geometry according to VSEPR model, it is octahedral. So the expected electronic geometry as per this steric number 6, it is octahedral OH. Okay, but when we look the actual geometry of the molecule, these bond pairs, 4 fluorine atoms occupying the planar face of the square. 1 2 3 4 fluorine. Okay, so it is forming a square planar geometry. Okay, and the 2 lone pair of electron in the sp3d2 hybrid orbital of the central xenon atom, they are occupying at the axial positions. Okay, and while dictating the shape of the molecule, we neglect these lone pairs, so that's why this is called as square planar geometry or square planar shape of the molecule. Okay, now the last one is xenon hexafluoride, that is XeF6 molecule. Okay, the remaining dictation will be same, only what will happen, this electron will migrate here, this electron will excite here, and this electron pair, one of the electron from this pair is get shifted to 3rd d orbital. Okay, and hence we have this is the situation, and that's why this type of orbitals undergo 1s 3p and 3d. So that's why sp3d3 hybridization. The central xenon atom in this XeF6 molecule undergoes sp3d3 hybridization. Okay, sp3d3 hybridization. Okay, and here we have to add one more orbital here. Okay, and with 6 fluorine atoms. Okay, so 1 2 3 4 5 6 fluorine atoms are sharing their electrons with the unpaired electrons of the central xenon atom, okay, and still it is carrying one lone pair of electron which is from the pi s, which is from the phi s subshell. Okay, so here number of lone pairs in this case is only 1. Number of bond pairs in this case is equal to 6. Here the steric number is 6 plus 1, 7. So according to VSEPR model, the 7 steric number suggesting the geometry of the molecule, that is pentagonal bipyramidal. Okay, pentagonal bipyramidal. But actually, due to the presence of only one lone pair and 6 bond pairs in this molecule, the geometry of the molecule or the structure of the molecule can be distorted octahedral. So this is the shape or geometry of the actual molecule. So this is central xenon atom, 1 2 3 4 fluorine. Okay, but the 5th and 6th fluorine atom, they are not exactly at the 90 degree. They are not exactly at the 90 degree to this plane. They are not exactly 90 degree to this plane, but due to the presence of lone pair of electron, this one lone pair of electron. Okay, this, to minimize the bond pair lone pair repulsion, this fluorine atom is not exactly at 90 degree, but it is somewhat distorted, and hence this bond can be written like this: fluorine. Okay, and hence we can show this. We can say the geometry is a distorted octahedral. This is distorted octahedral geometry of this xenon hexafluoride. Okay, so this is all about the structures of xenon fluorides. Now next point is the reactions of these xenon fluorides. We have started with types of xenon fluorides, then we have seen the synthesis reactions or preparation methods, then their structures, and now the last point is reactions of xenon fluorides. Actually, different types of reactions can be possible for these xenon fluorides, but the typical reactions that are given by these xenon fluorides, that we are going to see here. The first type of reaction is metathesis type of reactions. So the meaning of metathesis reactions in this case is displacement reactions. Okay, just like substitution reactions that we are studying in organic chemistry. Okay, so displacement type of reactions are called as metathesis reactions in this case. For example, this xenon hexafluoride XeF6. Okay, this xenon hexafluoride, when it is treated with water, okay, there is a formation of xenon trioxide. So one xenon atom is there, 3 into 1, 3 oxygen atoms are there. So there is a formation of xenon oxide plus 6 HF. 3 into 2, 6 hydrogen and 6 fluorine. 6 HF will be formed. So what type of reaction can be seen here? Metathesis. What do you mean by? Meaning is displacement. So here fluorine atoms in XeF6 are displaced by oxygen. So there is a bonding between xenon and fluorine here. It is displaced by xenon and oxygen. Okay, so and here the fluorine is get attached with xenon here. In the product, it is get attached to the hydrogen. So such type of displacement reactions, that is meant by metathesis reactions, can be seen here. Okay, another type of reaction is 2XeF6 plus silicon dioxide. Okay, so again 3 into 2 6 and 2 xenon here, so 2 XeO3, okay, 2 xenon, 3 into 2 6 oxygen, okay, so xenon oxide will be formed, and 3 SiF4, 6 into 2 12, 3 into 4 12, so silicon tetrafluoride and xenon trioxide will be formed. Such type of reactions are known as metathesis reactions. Then second type of reactions given by these xenon fluorides are oxidizing property. They are showing their oxidizing property. Xenon fluorides are strong oxidizing agents. Strong oxidizing agents. Strong oxidizing agents. Okay. For example, XeF2 xenon difluoride, when it reacts with water, how many molecules? 2 molecules of water, okay, gas and liquid. There is a formation of elemental xenon. There is a formation of elemental xenon plus twice HF, sorry, 4HF, so that's why we have to take here 2, 4HF plus O2, okay, so this is balance reaction. So xenon difluoride reacts with water, there is a formation of twice Xe, okay, so xenon will be formed. So what here, see, XeF2 molecule is acting as a oxidizing agent. It is a strong oxidizing agent. How it is acting as oxidizing agent? It is acting as an oxidizing agent means it is itself get reduced. It is get reduced. So why it is get reduced? Means its oxidation number is decreased. In this case, fluorine is mono having the charge -1. Okay, so 2 fluorine atoms are there. So total charge due to the F2 is -2, and hence xenon is carrying +2 charge. Xenon is having +2 oxidation state, or oxidation number of xenon in this case is +2, and it is get reduced to, so it is elemental xenon, so it is get reduced to 0. So this is decrease in oxidation number from +2 to 0. So that's why we call it as a reduction. So this molecule is undergone reduction, means it is acting as a oxidizing agent. So it oxidizes water to HF and O2. Okay, so such type of oxidizing reactions can be formed here. Then XeF4 xenon tetrafluoride, which reacts with platinum, okay, then it giving platinum tetrafluoride and elemental xenon, okay. So it is again strong oxidizing reaction of this xenon tetrafluoride. Then say third type of reactions that is given by this xenon fluoride is Lewis acid basic property. Lewis acid base type of reactions, okay. So Lewis acids means electron deficient species such as antimony pentafluoride, SbF5, antimony pentafluoride. When this xenon difluoride reacts with SbF5, okay, there is a formation of XeF SbF6, XeF SbF6. So this is a cation and this is a anion, okay. So this is acting as a Lewis acid, so hence it must be a Lewis base, okay. Means it is a fluorine donating agent. Fluorine donating agent will be acting in this reaction, and it is getting the fluorine from the xenon difluoride, okay. And this SbF6 minus, it can be it can be recovered or it can be observed in such type of complex cations and anion species. Okay, then reaction with Lewis base, such as F minus. Okay, so when xenon tetrafluoride reacts with F minus, that is fluoride anion, which is in the form of tetramethyl ammonium fluoride, okay. So this is cation, this is anion, totally it is neutral in nature. Okay, and this is quaternary ammonium salt, we can say quaternary ammonium salt. So 4 alkyl groups are attached to nitrogen, so hence it is carrying positive charge, OF minus. Tetramethyl ammonium fluoride is there, which is having F minus species. Okay, and when it is reacting with this xenon tetrafluoride, so F minus is here Lewis base, and hence this will be acting as a Lewis acid. Okay, and there is a formation of XeF5 minus, XeF5. So this F minus is get attached to this xenon, and there is a formation of XeF5 minus species. So this complex anion will be formed. Okay, so both these reactions, that is showing the ability to react with Lewis acids and bases, is similar to that of the interhalogens. Okay, the structure of this XeF5 is like this. Five fluorine atoms are in a plane. So why that's why we call it as a planar pentagonal geometry. Geometry of this anion is planar pentagonal. Okay, with a lone pair of electron, which is responsible for the minus charge. Okay, sorry, two lone pairs of electron on the just like XeF4 we know that it is carrying two lone pairs. Okay, so two lone pairs with 4 bond pairs, and the 5th bond pair with added fluorine. Okay, and it is total charge carried by this ion is -1. Okay, so this is the geometry of XeF5 minus, that is planar pentagonal. Okay, so this is all about the chemistry of xenon fluorides. Okay, in next lecture we will study about the xenon oxyfluorides, that is the compounds and reactions and their structures which are formed by the combination of xenon, oxygen and fluorine atom. Okay, so thanks for watching this video. Have a nice day.